Cairo monorail. The Cairo monorail is the longest driverless monorail system ever built, running above a metropolitan area of 20 million people across two lines, totaling 96 kilometers of elevated concrete guideway. Each four-car Alstom 300 train operates at 80 kilometers per hour, and the system is designed to move 45,000 passengers per hour in a single direction, equivalent to 20 additional highway lanes without acquiring a single square meter of ground-level land. A journey across the East Nile line takes approximately 60 minutes for a distance that takes up to 3 hours by car during peak congestion. The system operates under grade of automation 4, meaning no driver is present at any point. Its primary function is connecting central Cairo to the new administrative capital, a satellite city 45 kilometers into the desert that has no viable commuter link without it. HS2. HS2 is the largest infrastructure project currently under construction in Europe, covering 230 kilometers of dedicated standard gauge track between London and Birmingham, engineered for a maximum speed of 360 kilometers per hour. The Chiltern Tunnel runs 15.8 kilometers beneath protected landscape at depths reaching 80 meters, and the Northolt Tunnel adds another 13.5 kilometers beneath West London. Where the route passes through protected areas, green cut and cover construction is used. A trench is dug, track is laid, and the trench is sealed with soil and replanted, so the surface returns to farmland or woodland. The route requires more than 8,000 separate environmental consents. In October 2023, the government cancelled Phase 2, ending the planned extensions to Manchester and Leeds and reducing the project from a national network to a single corridor. The trains, designated Class 895, are designed to operate on both the new high-speed line and the existing West Coast Main Line. Brightline West. Brightline West is the first privately financed high-speed rail line in American history, and it runs through the central reservation of Interstate 15 for the majority of its 351-kilometer route between Las Vegas and Rancho Cucamonga, California. That alignment was secured through a 50-year lease from state highway authorities, eliminating most of the land acquisition process that has blocked previous American rail proposals. The 10 Siemens AP 220 train sets are each 7 cars long, carry 450 passengers, and operate at up to 320 kilometers per hour, reducing a journey that takes 5 hours by car during weekend peak periods to 2 hours and 10 minutes. Construction began on April 22, 2024. Total project cost reached $21 billion, rising from an original estimate of $12 billion, and Brightline has applied for a $6 billion federal loan to cover the difference. A dedicated manufacturing facility in Horseheads, New York, is conditioning the trains for sustained operation in Mojave Desert temperatures before delivery. Mumbai-Ahmedabad High-Speed Rail. The Mumbai-Ahmedabad corridor is the first deployment of Japanese Shinkansen technology outside East Asia, running 508 kilometers between India's financial capital and its industrial center. Of that distance, 353 kilometers sits on a continuous elevated viaduct, the longest elevated rail structure on the planet, while a 21-kilometer tunnel beneath Mumbai includes a 2.1-kilometer section running under the sea at Thane Creek. The 24 E5 series Shinkansen train sets are rated for 350 kilometers per hour and have been modified with reinforced sealing and upgraded cooling systems to operate in monsoon, humidity, and summer temperatures, exceeding 50 degrees Celsius. The current fastest service on this route takes between 7 and 8 hours. The high-speed line reduces that to 2 hours and 7 minutes. Japan financed 88,087 crore rupees of the project through a 50-year loan at 0.1% interest, structured alongside technology transfer agreements that allow India to manufacture its own high-speed rail components domestically before the project is complete. CRRC 600. The CRRC 600 is a magnetic levitation system designed for 600 kilometers per hour, with a prototype that reached 623 kilometers per hour in testing. It uses electromagnetic suspension, where magnets on the underside of the train are attracted to the guideway above, maintaining a levitation gap of 10 millimeters with no wheel contact and no mechanical friction between vehicle and track. Propulsion comes from a linear, synchronous motor embedded in the guideway, generating a traveling magnetic field that pulls the train forward. At operating speed, a Beijing to Shanghai journey of 1,000 kilometers takes roughly 2.5 hours, competitive with air travel when airport processing is included. The system requires purpose-built track with no compatibility with China's existing 40,000-kilometer high-speed rail network, and the original Shanghai maglev, which uses related technology, has operated at a financial loss since 2004. Chuo Shinkansen. The Chuo Shinkansen will operate at 505 kilometers per hour through tunnels running 1,400 meters below the Japanese Alps, with 90% of the 286-kilometer Tokyo to Nagoya route underground. The superconducting magnets are cooled by liquid helium to negative 269 degrees Celsius, 4 degrees above absolute zero. Below 150 kilometers per hour, the train runs on retractable rubber tires. Above that speed, magnetic repulsion between onboard magnets and guideway coils lifts the vehicle 100 millimeters clear of the surface. The existing fastest Shinkansen service between Tokyo and Nagoya takes 100 minutes. The Chuo Shinkansen takes 40. Total infrastructure cost exceeds $82 billion. Construction permission for the Shizuoka Prefecture section was withheld in 2020 over hydrological modeling, showing that tunneling would divert 2 cubic meters of water per second from the Oi River, affecting downstream agricultural supply. That dispute has moved the completion date from 2027 to no earlier than 2035. HART Hyperloop. The European Hyperloop Center in Groningen operates a 420-meter full-scale test track, and its central engineering focus is switching. Every functioning rail network depends on mechanical points, physical sections of movable track that redirect vehicles between lines. But at Hyperloop speeds of 700 kilometers per hour, mechanical switching is not feasible within the stopping distances involved. HART's solution places the switching mechanism on the vehicle rather than the infrastructure. Active magnetic components on the pod interact with passive guideway elements to redirect it between tubes without any moving parts in the track and without reducing speed. A pod exits the main line and enters a branch at full operating velocity. This is the prerequisite for a network rather than a single point-to-point route, and HART completed its first successful switching test in September 2024. The project operates under an open specification model, so pods from different manufacturers and infrastructure from different member states are designed for mutual compatibility from the outset. Future Hyperloop. Future Hyperloop, incubated at IIT Madras, holds the first signed commercial contract for Hyperloop technology anywhere in the world, and the application is freight rather than passengers. In 2026, the Deandale Port Authority at Kandla commissioned a pilot system to move 40-ton shipping containers 8 kilometers from dockside to inland loading bays, bypassing the truck queues that currently reduce throughput across the facility. The initial phase uses linear induction motors and battery power charged by on-site solar panels, with pods running on a physical track rather than levitating, allowing the system to be validated against the salt, dust, and mechanical vibration of an active industrial port, before progressing to magnetic levitation and reduced pressure tubes in later phases. The test track at IIT Madras runs 422 meters, the longest student-operated Hyperloop facility in Asia, and the Kandla installation is the first instance of Hyperloop technology moving from demonstration to a contractual delivery deadline with a paying client. T-Flight. The T-Flight is developed by China Aerospace Science and Industry Corporation and is structured around 3 speed targets: 1,000 kilometers per hour in Phase 1, 2,000 in Phase 2, and 4,000 in Phase 3, which corresponds to Mach 3.2 and exceeds the operational speed of the SR-71 Blackbird reconnaissance aircraft. The system places superconducting maglev pods inside evacuated tubes, removing 99% of aerodynamic resistance. The levitation gap is 100 millimeters, 10 times wider than the CRRC 600, because stability at supersonic ground speed requires clearance that a narrower gap cannot reliably maintain. A 2-kilometer test track in Datong achieved 623 kilometers per hour in late 2024, and a 60-kilometer full-scale test line is under construction. Track flatness must be maintained to within 0.3 millimeters across the full length. At 1,000 kilometers per hour, the journey from Wuhan to Beijing covers the distance in under 15 minutes. The primary unresolved engineering problem is tube integrity. A structural breach at Mach 3.2 in a near-vacuum environment produces immediate and total vehicle loss, and no publicly demonstrated mitigation system for that failure mode currently exists.